All right, welcome back. We are now at lecture 3, and this is going to be part 2. And part 2 really is going to teach you how to solve for Kc and Kp. Okay, and we talked about Kc in the last video, and we said that it's the equilibrium constant expression, wherein we have a ratio of the products over the reactants. And Kc as a value, if it's larger than 1, it'll tell you that it's mostly products. If it's less than 1, it'll tell you it's mostly reactants. And if Kc equals 1, then it's a mixture of about half and half products and reactants. So, in this particular video, we're going to actually use real numbers and calculate what is Kc in experimental data conditions. Okay, so if you look at this example here, you have experimental molar data, and you can calculate Kc. Okay, you're going to reconsider example 14.1 from the last video, and this reaction was done in a 10-liter flask. Okay, so this is important because remember from that reaction or that example, everything was in moles. Okay, so to calculate Kc, really you need, and just a review here, you need products. Products is CH4. Okay, and H2 over reactants, which is CO and H2. Okay, and because there is a 3 in front, remember we have a 3 as our exponent. Okay, and it is very important to remember that these brackets, okay, really stand for molarity. Okay, so it's the molarity of CO, the molarity of H2, and so on and so forth. And remember, molarity is from chapter 12, moles over liters. So based upon the fact that we have what they gave us, or we actually found the molar composition in the previous video, okay, all we need to do to convert to molarity is to divide by the reaction vessel volume. In this case, it is 10 liters. So if we did that across the board, okay, we're going to, dividing by 10 is really just moving the decimal point 1 over to the right. So if you would like to do it on your calculator to confirm, it's fine. But really, we're just going to move that decimal over to the right. And so this is the molarity at equilibrium. Okay, these 4 numbers here. Okay. So really, now we're going to use these 4 numbers, and we're just going to plug it into our Kc. Okay. So really, it is 0.0387 times 0.0387 times 0.0613 times 0.1839, and this is to the 3rd power. Okay, if you do the math all the way through, you should get 3.91. Okay, 3.91 is slightly greater than 1, so we would say this is mostly, or maybe more is a better word, more products than reactants. Okay, that's all that the number means. There's slightly more products than reactants at equilibrium. Okay, so let's do another practice just to get some feeling for how to do these problems. You have hydrogen iodide decomposes to H2 and I2. Okay, and so let's read the problem. It said the amount of I2 in the reaction mixture can be determined from the intensity of violet color of I2. So they've obviously done a spectroscopy experiment similar to what we've done in the lab. Okay, so the more intense the color, the more I2 you have, because I2 is a violet or purple color. Okay, so when you have 4 moles of HI and is placed in a 5-liter flask, okay, the equilibrium mixture was found to contain this much I2. So this is at equilibrium. This is initial. Okay? And so they ask you, what is the value of Kc? Okay? So to do this, we're going to have to set up our little table. Okay? And I don't know if you remember this from last time, but I like to use initial instead of starting, because then the acronym becomes ICE, I-C-E. And so in the homework and in the notes that I write, oftentimes instead of writing initial, change, and equilibrium, I'll just write ICE, I-C-E. Okay. So basically, we're going to set up this little ICE table that we have. Okay. And at the beginning, we have 4 moles, and it's in a 5-liter flask. So the concentration or the molarity of HI is 4 divided by 5. 4 moles divided by 5 liters. That comes out to 0.800 molar. Then at equilibrium, and this is at equilibrium, okay? This is initial, okay? You have 4.442 moles, and again, it's still in that 5-liter flask, so you get 0.0884 moles per liter, or molarity. Okay, so let's plug in these two numbers. This is HI initial, so initial is here, HI is here, so it's going to be 0.800. Okay, that's the concentration. Okay, you have none of the H2 and none of the I2 at the beginning. Because those are products. Okay, the change is going to be minus, be careful, because of the 2 here, it's minus 2x, okay, and again, it's minus because it's a reactant and it's getting used up, okay, and then we're going to have plus x and plus x, because those are products, those are plus. So at equilibrium, we're going to have 0.800 minus 2x, we're going to have x, because 0 plus x is just x, and 0 plus x is just x. Okay? But we do know that I2 at equilibrium is 0.0844. So at equilibrium, okay, the I2 is here, x, right? That is equal to 0.0884. Okay? So now that we know x, we're just going to plug everything in. Okay? So if you have 0.8 minus 2x, and x is 0.0884, okay, then really this comes out to 0.623 capital M of HI. Okay, here x is just 0.0884 M of the H2. And of course, this is of the I2. Okay, so how do I calculate Kc? I'm going to switch to a different color. Kc is products, so that's the I2 and the H2. So really, Kc is going to be 0.0884 times 0.0884. This is the H2, this is the I2. Okay. Divided by HI is 0.623. This is the IHI. Okay, and remember it is squared. Okay, because of this 2 here. Okay, so therefore, if you do all of this, okay, it comes out to 0.0201. Okay, and again, what does this really mean? This is a number that is less than 1. Okay, because it is less than 1 at equilibrium, okay, it is mostly reactants. Okay, let's do one more exercise so that we have a good feeling for how to do this. Okay, so and as we read, I would highly suggest, okay, you do what I did in the previous slides. Okay, you get out another colored pen and you tell yourself, what is this number? Okay, when you have 1.00 moles of H2, okay, and it was put into a 10-liter vessel. Because it was put into a 10-liter vessel, this is obviously initial. Okay, it gave an equilibrium mixture containing 0.0285 moles of H2. Okay, it says equilibrium mixture. This is at equilibrium. Okay, and they want to know what is Kc. Okay, so again, it is in a 10-liter flask, so we're just going to calculate the molarity real quick. For the H2S, it's 0.100 moles divided by a 10-liter flask. Okay, so really it's just moving the decimal point 1 to the right, so it becomes 0.01 1, 0, 0. Okay. And then for your molarity of H2, it's 0.0285 moles over 10 liters. So this becomes 0.00285. Okay. And remember, this is initial, so that goes at the beginning. Okay. So this is 0.0100. You have no products. Okay. The change is minus 2x, and again 2x because of the 2 in front, and it is plus 2x, and again we have a 2 in front, and plus x. Okay, so at equilibrium we get 0.0100 minus 2x. We get 0 plus 2x, or just 2x, and 0 plus x is just x. Okay, and they tell you that the molarity of the H2 at equilibrium is this number. Okay, so remember, at equilibrium, the H2 concentration, that's this guy, okay, is equal to this number. So really what we're saying is 2x is equal to 0.00285. Okay, again, I repeat, this is the concentration of the H2 at equilibrium. Okay, and 2x is the concentration of H2 at equilibrium. Okay, so therefore 2x is equal to this. So because of that, x is equal to 0.0028. Let's see here. X is equal to 0.00143. Okay, so I'm dividing this side by 2. I'm dividing this side by 2. I get that. Okay, so now that I have x, okay, I'm going to plug it into here. And I'm going to plug it into here. And you can plug it into here as well, although you already know what that is. It's already the 0.00285. Okay. So doing that, I'm going to get three numbers. I'm going to get 0.0072 molar of the H2S. I'm going to get 0.00143, sorry, times 2. So that's going to be 0.00285 molar of the H2 and 0.0143 of the S2. Okay, so therefore to calculate Kc, I'm getting products over reactants. I'm going H2 to the 2 because of the stoichiometric coefficient, S2 over H2S, and again it's squared because of the coefficient in front. So I'm going to plug in all my numbers. 0.00285 squared times 0.00143 over 0.0072 squared. Okay, this comes out to 2.3 times 10 to the minus 4. Minus 4 is a very small number, so it is mostly reactant. Okay, notice in all of these examples, I have left off any units when it comes to calculating Kc. Kc, depending on the reaction and the coefficients, will have various not weird, I wouldn't say weird, but various units like m squared, m to the minus 1. So when we've reached this point in the book says, Kc, no need for units. Okay, so whenever we're calculating Kc, no need for units. Really, it's just a number that represents the ratio of products to reactants. There really is no need to put in a unit there because we're really looking at it and going large number, small number. So again, this is one of the happy times where you don't need to put units for this variable Kc. All right. One more exercise and then we're going to move on to Kp. Okay. And if you want, you can pause this video so that you can get some practice doing it yourself and then seeing if you get the same answer that I do. Okay, so hopefully you've paused the video and done that. So let's read the problem. A mixture of 1.16 moles of A and 1.35 moles of B and 0.641 moles of C are placed in a 1 liter flask. These are all initial concentrations or initial molar amounts, okay? And it's allowed to reach equilibrium, and at equilibrium there is 195 moles of A, okay? So notice here, there is actually more A than we started out with, meaning there's a shift of the equilibrium to the right, okay? So again, it is in a 1 liter flask, so really dividing by 1 gives me the same numbers. So I'm just going to rewrite the numbers as molarity. Molarity of A initially is 1.16 molar. B is 1.35 molar. C is 0.641 molar. And A at equilibrium is 1.95 molar. Okay, I've indicated whether it's initial or equilibrium with these 0 for initial, just like in the previous chapter, and EQ for equilibrium. Okay, so initially, all right, initial here, the concentration of A is 1.16. Okay, concentration of B is not 0, it is 1.35, and the concentration of C is 0.641. Okay. And since it is a shift to the right, okay. Sorry, it is a shift to the left, shift to the left, my bad. It is shifting more towards to the left to the reactants, okay. So really we're going to say this is equal to 2x, or plus 2x, sorry. Okay, this is minus 2x, and this is minus x, okay. Notice that the signs are reversed here because you have more of the A than you did initially. Okay, this becomes 1.16 plus 2x. This becomes 1.35 minus 2x. And this becomes 0.641 minus x at equilibrium. Okay, and they tell you that the concentration of A is 1.95 at equilibrium. So really, equilibrium A is this number here. So 1.95 is equal to 1.16 plus 2x. Okay, I'm going to subtract 1.16. Okay, that cancels that out. I get 2x on this side is equal to 9 minus 7, 0.79. I'm going to divide both sides by 2. I believe this comes out to 0.4. So I'm going to round it to 0.4. Okay. So now that I have x, I'm going to stick it in here, here, and here. Okay. This is going to get me 1.95 molar here, and 0.55 molar here, and 0.24 molar here. Okay, that's my molar composition. So Kc is products divided by the reactant. Okay, so this comes out to 0.55 squared, 0.24, okay, divided by 1.95 squared. Okay, this comes out to 1.9 times 10 to the minus 2. Okay, and again, mostly reactant. This is a really challenging problem. Normally, I wouldn't put this kind of problem on exam of a reverse equilibrium, but it does happen where you mix 3 things together and the equilibrium shifts to the left instead of to the right. Okay, equilibrium can shift left or right depending on what you add to the flask. All right. The equilibrium constant Kp, okay? Now when dealing, so far we've been looking at just molar concentrations in terms of moles per liter. But when it comes to dealing with gases, a lot of times it's often easier, instead of measuring concentration, it's just easier to measure the partial pressure. And because with a gas, you can just measure the pressure that the gas container has. And so you just put on a pressure gauge and then just read the pressure gauge. So it's easier than the spectrometer where you have to take the absorbance and then figure out the concentration based on your line like we did in the first lab in the semester. Okay, so a lot of times, because it's easier to do that, okay, we use this term called Kp, okay, and all it is saying is that with gases the concentration is proportional to the partial pressure. So if you increase the concentration, you really increase the pressure, okay. So the less concentrated it is, the lower the pressure. The more concentrated it is, the higher the pressure. And they give you an example here. This is less pressure, it is less concentrated. This is more pressure because it is more concentrated, okay. And because of this, you know that PV equals nRT from the ideal gas law. If you rearrange that equation, N over V equals P over RT, okay. So N over V, remember, is just moles per liter, because N is moles, volume is in liters, okay. So really the molarity is equal to the pressure divided by RT. Since R is a constant and T is a constant and temperature is a constant in all of our reactions, really the molarity is equal to the pressure, or proportional to the pressure. So if you increase the moles per liter, you're increasing P. And so basically you can replace all of your concentrations with the partial pressure. So let's see how you would do that. And again, it's very, very simple. If you look at the equilibrium expression Kc, it's products over reactants. Kp, same thing. It's going to be products over reactants, but instead of the concentration, we're going to say P, and this stands for the partial pressure. Okay, so it's the partial pressure of the CH4 times the partial pressure of the H2O divided by the partial pressure of the CO and the partial pressure of the H2, and again you have this to the third because you have a coefficient of 3. Okay. Now, although Kp and Kc are not equal, they are related to one another, and the book gives you this equation: Kp equals Kc times RT to the n, or delta n actually, and the delta n is really the change in moles. Okay, so really it's the sum of the moles of product subtract the sum of the moles of reactants. Okay, and it's very easy. If you look at this previous example here, the moles of the product are here, right? This is the product. You have one CH2, one H2O, because there's a no number in front of these. So you would say you have 2 moles of the product. The reactants, you have 3 and 1 of 3 of the hydrogen, 1 of the CO. So really 3 plus 1 is 4. So you have 4 moles of the reactants. So really delta N in this particular example is 2 minus 4, or just minus 2. Okay. R is just the gas constant, T is just the temperature, and Kc is just the equilibrium constant expression that we have been calculating since the beginning of lecture 3. So let's look at an example. Okay, it says phosphorus pentachloride interconverts to phosphorus trichloride and Cl2 gas. Okay, so if Kc equals 3.26, okay, times 10 to the minus 2, we're going to plug that under no. Okay, and it is at 191 degrees Celsius, so we're going to change that to Kelvin. So 191 plus 273 is 464. R is the gas constant that we know and love, 0.0821 liters atmospheres over kmol. We've done this many, many times, hopefully, for the ideal gas law. Okay, and in this particular reaction, delta N is, again, the moles of products minus the moles of reactants. In this case, there are 2 moles of product and 1 mole of the reactant. So we're going to say product is 2 moles, reactant is 1 mole. So we're going to plug in all of these numbers. We have our Kc, we have our R, we have our T, we have our delta N. Okay, and doing all this through, if you plug it in your calculator, you should get 1.24. Okay, so this is how you would calculate Kp instead of Kc. And really, it's just an easier way when we do this in lab, because oftentimes we would like to measure the pressure rather than the concentration using a spectrometer. All right, this is the end of Lecture 3, Part 2. Really, there is two main things going on in this video. You would like to remember how to calculate Kp. You will have homework problems on this. You will have to write Kp expressions, okay? And remember, it's very simple. It's still products over reactants. You're just replacing the concentration with the uppercase P. P stands for partial pressure. And of course, you need to know how to calculate an actual number for Kc given initial data and data at equilibrium. All right, this is the end of the video for Lecture 3, Part 2. I would stop here and I would do the corresponding homework in your homework booklet.